Intel's got some GPU news today. It's a really straight shooter news video, pretty simple. They've got an Xe3 GPU that they're detailing. This is in Panther Lake, so it's rolling out in mobile and in handheld devices first. And it probably starts to set the framework for what we might see in a DGPU launch. It's not 100% clear yet what they're planning to do with Celestial. This isn't Celestial yet, but it is an iteration moving from Xe2 to Xe3. They've made some changes, and it gives us a pretty good indication of where Intel is going right now and focusing for its GPU solution. So let's get into that. The biggest change to Xe3 is that it's just larger, with render slices scaling up to more Xe cores per slice, an increase in L1 cache, with Intel referencing 192 kilobytes going to 256 kilobytes now, a significant increase in L2 cache, and more registers that are better utilized. Micro benchmarks show significant improvements in things like occluded primitives culling for unnecessary triangles when rendering game scenes, in addition to improvements in anisotropic filtering. So the micro benchmarks are showing some high Z improvement, high Z handling improvement, which culling primitives is not a new thing, obviously been around forever, but this is clearly an area where Intel has had a lot of ground to gain, and from what they're showing at least, it looks like they're gaining some of that. Now, whether that works in reality outside of a micro benchmark, we'll need to test it to see, and as soon as we can, we'll have reviews of the hardware. Most likely, we're going to wait until Celestial on DGPU side, though, and not test the laptops. But anyway, there are some other changes here, too, that are significant. So they're also moving to variable register allocation, and they're changing some of the register count in general. So this is supposed to unclog some of the pipeline, where one of the biggest limitations Intel has had with Xe2 and with Battlemage and Alchemist has been underutilization of its resources. So Intel's hardware has had a lot more to offer than sometimes it seems like is actually being used, as opposed to something like NVIDIA, where NVIDIA does a pretty good job at keeping its hardware utilized as long as other system resources don't jam it up. For the most part, it's not always true. Look at VRAM, for example. But Intel noted to us that it is also working on driver and software improvements. This includes improvements to the control panel, plus some AI and NPU hardware. We don't really cover laptops too much. That stuff will find its way into handheld gaming devices, though, which we do cover. So we'll go over a little bit of that, plus Xe3. So all this likely indicates where Intel's going next for its future DGPUs and its Celestial architecture whenever that happens. They did announce an Xe3P architecture, or at least IP branding name. They didn't have any details whatsoever about it. Our understanding, or our impression we got, is that that's maybe Celestial, or at least Celestial Mobile or something. But anyway, I asked why Xe3P, what does that mean? And they said it's plus. So old Intel habits die hard, I guess. I'm looking forward to, just like when they did 14 nanometers plus, and then later they did 14 nanometers plus plus, actual name by the way, I'm looking forward to when they go from Xe3P to Xe3PP. It sounds... Before that, this video is brought to you by the Height Y70 Touch Infinite. We previously reviewed the Height Y70 non-touch series and found its overall build quality to be good and competitive. Now, the Y70 Touch Infinite ships with a custom 14.9-inch IPS touchscreen with a 60Hz refresh rate. The screen connects to your system build and can be used as a showpiece on the angled corner front panel, displaying stats, music players, videos, and more. Height's entire Y70 series now also includes multiple new colors, like the Taro model that you're seeing here. Learn more at the link in the description below. All of this follows the announcement that NVIDIA is investing into Intel, including specifically for future mobile components, where NVIDIA even said that it will cross-license or collaborate with Intel on future RTX chiplet integration into some of Intel's mobile products. None of that is in here today. This presumably was all kind of done well before that deal was announced. Briefly on the naming, Intel said that its naming is confusing between Xe, Alchemist, Battlemage, Celestial, Druid, and so forth, and it was careful to note that these parts are not an iteration on the branding side past Battlemage, and I guess they're going to talk more about that later, but these are going to be called Arc B series on the laptops, despite being Xe3, not Xe2. So I honestly, it's going to get even more confusing now, because we're mixing different IP iterations on the same naming. But anyway, Intel specifically mentioned designing Xe3 to scale to larger configuration sizes, and this would be good news for anyone who wants to see larger than B580 type card in DGPU if they apply this also to the DGPU side in the future. I do want to address this. We have a major methodological overhaul involving animation error, simulation time error for benchmarking. We're not going to go into. It's very interesting. The video is almost done. It'll be out soon. Let's get into the micro benchmarks first. and then we'll look into the block diagrams. This is a chart of micro benchmarks, which are workloads designed to target extremely specific functions or behaviors on a product. A 2x improvement here won't equal a 2x improvement in most real-world applications, but these allow us to see where the improvements are appearing, at least according to Intel directly. Intel published these for Xe2 previously as well, so we can see the trajectory they're on. In Xe3, for the depth writes category, Intel says it saw a 7.4x relative improvement normalized to clock frequency. This is not isolated for configuration size, so this means that it's not a perfect comparison since Xe core count is different between Xe2 and Xe3 in these tests. This 7.4x improvement outstrips the change in configuration size though. We asked Intel what depth writes means. The company told us that it's related to high Z culling, which you've likely heard of before, and that this bar represents better primitives culling in the pipeline, meaning culling of unseen triangles and geometry sooner in the pipeline so as not to waste resources rendering unseen objects in game. An example might be if a building is obstructing a player. There's no point rendering the player if it can't be seen. Culling isn't new, and batching primitives in ways that eliminate occluded primitives has been around forever. But this shows that there's still plenty of ground to gain here, at least for Intel. This will result in better utilization of resources and allocating them to more productive work if it can scale. Intel told us that the improvement to this process is disproportionately beneficial, meaning that it thinks it should have an impact in gaming performance that would be more noticeable than some of the other improvements. We'd expect this to carry over to the future Celestial DGPU parts as well. The high register pressure shader section also saw uplift in micro benchmarks at 1.9x to 3.1x depending. Scattered reads improved by 2.7x on the relative scale of time, with Intel noting to us that this has to do with using samplers to read data scattered across something like, their example was a texture, as opposed to a well-organized data set. Mesh rendering is also shown here, with Intel telling us that Xe2 had already provided a proof of concept around improving mesh shading. Now they're representing mesh rendering, and Intel noted that this micro benchmark is representative of workloads where a lot of polygons are present, telling us that the uplift comes from a larger cache and more efficient use of its registers in those polygon or primitives intensive workloads. Culling also contributes here. You might see a large benefit here with really dense meshes. Quickly as well, Intel also saw uplift in anisotropic filtering, which is the old function that helps improve smoothness of textures and objects proportionate to the view frustum's angle. Ray triangle intersection also improved by 2x in the micro benchmarks on relative scaling, which is noteworthy since Xe2 had already benefited from ray tracing improvements. Looking back at the Xe2 micro benchmarks, Intel then highlighted Draw Xi and Compute Dispatch Xi primarily. At the time it talked to us about this chart, Intel told us that this was due to the implementation of native execute indirect support for indirect draw and dispatch, as opposed to its Xe1 predecessors' emulation of these functions. So this stuff remains in Xe3, the improvements that is. Time to get into block diagrams for how the new Panther Lake Xe3 block is constructed. This shows a 12 Xe core configuration as the maximum size announced for mobile so far, or possibly ever, with this configuration carrying 16 megabytes of L2 cache, 2 geometry pipelines, 12 samplers, and 4 pixel backends. The L2 cache is noteworthy here, and the configuration size will almost certainly be larger with DGPU parts, although they might differentiate themselves from what we're looking at today. This is the new Xe3 render slice. A render slice is Intel's terminology that defines a block in the GPU containing Xe cores. For reference, the Battlemage B580 with Xe2 has 20 Xe cores on 5 render slices, so each slice is only one part of the total GPU. The Xe2 slice had 4 Xe cores each previously, with Xe3 moving to 6 Xe cores per render slice. Intel also intends to scale up the configuration size on mobile to again a max of 12 Xe cores, or that'd be 2 render slices, up from 8 Xe cores on a prior 2-slice configuration. The Xe3 render slice shows that each Xe core has 8 vector engines, which is unchanged from Xe2 cores. However, Intel is increasing the cache size in Xe3. Intel's Tom Peterson stated this, quote, "The first thing we've done is increase the size of our L2. By increasing the size of the L2 from 8 megabytes to 16 megabytes, we reduced the traffic that hits the memory interface. That's important because the memory interface is typically one of the most precious resources on a graphics chip. We can see anywhere between 17% and 36% traffic reduction heading towards memory, which has a significant performance effect on these different applications," end quote. Looking at Intel's first-party results, it presents the improvement in the form of relative traffic on the SoC fabric in the vertical axis against the baseline 8 megabyte L2 cache. Cyberpunk with RT showed a 19% reduction. Black Myth, rasterized, showed a 36% reduction. and the rasterized Steel Nomad test showed a 17% reduction. Intel also told us that Xe3 increases L1 cache by 33%, noting a move from 192 kilobytes to 256 kilobytes. When we asked Tom Peterson which area of uplift he thought had the most impact on overall performance, but in particular gaming, he pointed us toward the register and thread changes. Intel has increased thread count upwards of 25% depending on configuration and has moved to variable register allocation. Peterson noted that occupancy of the compute units, including on Battlemage, previously wasn't always high, despite them being available for work, meaning that there was more GPU hardware present than was being properly utilized by applications. This is actually something we talked about with Tom Peterson previously when we did our driver discussion with Intel a while ago. So we've been talking about for a while in the community how Intel's GPU hardware's biggest limitation seems to be on the software side and not being utilized, but they can also do things on the hardware side to try and improve that, and that's one of the things they're trying to improve here. Intel has focused on this in both drivers and hardware, and he noted that previous register allocation and thread count choices would, quote, starve the pipeline if the shader used too many registers, end quote, which is being addressed. The ray tracing unit also got improvements. Intel says it, quote, slowed down dispatches of new rays while the sorting unit catches up, end quote, citing out-of-order dispatch and triangle testing. The ray tracing unit improvements seem to be largely attributed to asynchronous dispatch test processes. Intel also highlighted a new URB manager as part of its fixed function enhancements, which is also where we find the anisotropic filtering uplift attributed. Peterson said this, quote, we also now have a new URB manager, which allows partial updates versus flushing the whole thing. Our URB structure is where we pass results between our units inside the GPU. It used to be somewhat of a serializing point. Now we can actually use that, partially, without flushing each complex, end quote. We thought these next couple slides were pretty interesting as well. Intel showed a frame on Xe3 versus Xe2, frame here being like a literal frame from a video game. These are not normalized for configuration size, so it's not a perfect like-for-like comparison, and it shows a 12-core versus 8-core configuration as a result, which disallows a perfect like-for-like inspection. However, it is ISO frequency and ISO power, so it's normalized for frequency and power. The horizontal axis is for API call execution, with the vertical axis being milliseconds of time to execute across a single frame being drawn for the duration of this test. Higher is worse. This is for Cyberpunk 2077. Of note, Intel shows an 8 millisecond reduction to Xe3 with the compute and pixel shader section towards the end, assigning some of that uplift to the change to the variable registers and L1 cache size increase. We can also see that according to Intel, the L2 size increase benefits the render base pass with a 0.39 millisecond improvement, preceded by the move to 10 threads and variable registers, providing a 2.93 millisecond improvement in the pre-pass. More broadly, Peterson told us in a call that the register allocation and the number of threads would starve the pipeline if the shader used too many registers previously, as stated a moment ago for a different topic, but that's also being partially addressed here. He said that the previous architecture could cause a reduction in the utilization of available compute resources, continuing on the previous subject, due to the regular flushing of the pipeline due to regular reallocation into memory. This image is pretty cool though. It's what actually happens in a frame when it's being drawn. You can't really get these perfectly represented and broken down into the literal individual pieces, but they've done about as much as anyone can do here, and the first-party vendors are going to have a lot more insight into what's going on in the core than anyone publicly, just the tools don't exist. So it's always cool to see this kind of stuff, and we have a full video talking about this type of frame previously. Intel's next major area of focus was on power delivery and power management. They cited learnings from the MSI Claw launches, and it mostly comes in the form of proper resource allocation for power budget, particularly between the CPU and the GPU when running a game. This should benefit laptop and handheld devices in particular that have a limited power budget to be split between the two. Intel noted that previously, a lack of application awareness meant that the device could sometimes divert too much power to the CPU, leaving the GPU bottlenecked on its power limit, while the CPU offered a level of performance that wasn't being kept up with by the GPU. Intel gave the MSI Claw as an example of a time that this didn't work out well. The company noted that it improved on this earlier in the year with its Intelligent Bias Control V2. And now it's introducing a V3 to build upon that. As for V2, the problem it was addressing was that previously the application was not necessarily known to the device when it was managing the power, in this case, a game. Intel said that software and hardware wouldn't correctly balance the workload between the CPU and the GPU, resulting in stuttering due to the power being starved. Intelligent Bias Control v2 took GPU heuristics and utilization metrics to then inform thread scheduling and resource assignment at the operating system level. Intel hadn't really talked about this much, but they did market improvements to 1% and 0.1% low metrics via better frame interval pacing as a result of this change. The new v3 version of this today adds E-core first scheduling. This is self-explanatory in that the E-cores get the scheduling first when gaming. Now this sounds worse on a desktop, it probably would be, but Intel says that the end result is reduced power diversion to the CPU by using lower power cores prior to the P-cores. These are also lower performance, but it should free up the shared total power budget to go more toward the GPU instead. In GPU-bound scenarios particularly, like many games on handheld devices, this is a better outcome in theory than burning power on a component that isn't as burdened. This comparison between Panther Lake and the prior generation of the bias control solution shows that peaks in power utilization have smoothed out while the GPU power consumption has leveled to be more predictable. Now, this is a first-party test. This is something that we'll be somewhat able to produce as a chart when we get some of these handhelds in, or we could potentially look at the last gen of them to get an idea. But the GPU is also getting more total power budget, at least as a percentage, than previously in this example chart. It reduces the CPU power in exchange for that, but if the CPU power is not being productive and is actually causing stuttering, then that's fine. For GPU-bound scenarios in particular, this should be a better outcome. It might help in some CPU-bound scenarios as well. All of this, as a reminder, is first party, so we'll need to validate independently, but this is at least what they're claiming. Although Intel had a few other things for this event, we'll just focus the last point here on XeSS. So Intel also announced XeSS3, which includes XeSS multi-frame generation, or XeSS MFG. A few more letters here, and they'll have a whole alphabet. XeSS MFG is conceptually similar to NVIDIA's MFG. XeSS MFG takes 2 real frames to calculate optical flow networks using motion vectors and the depth buffer. Then it uses that information to generate up to 3 frames between the 2 real frames. The frames are then displayed in order and paced in a way to minimize animation error. And we'll have a full separate deep dive on our new animation error testing methodology within a day or two, so check back for that. It's a pretty big undertaking. The new XeSS frame generation override setting in the driver software allows the user to set 2, 3, or 4x mode. Intel presented a few timelines of a single frame, one at native and then several with various levels of XeSS technology in use. The shorter the duration that the frame is on the x-axis, the less time the frame took to complete. The top half of each shows the instructions, and the bottom half shows when the geometry pipeline is active. Compared to native, the raster, RT, and denoise sections of the frame are shorter on the XeSS3 timeline due to rendering at a lower resolution. The first purple section represents XeSS SR to perform the upscan. We've accumulated even more letters. The second purple block starts with the optical flow portion of FrameGen, followed by 3 frame generation operations. It seems like Intel's argument is that the entire FrameGen process takes less time than drawing 1 real frame or something, and is therefore better, or something. But this totally ignores image quality. We've shown with both AMD FMF and NVIDIA MFG that the image quality sacrifice isn't always worth it. Sometimes it is, but it's not as simple as always being that way. Intel stated that these frames upscaled with XeSS SR are the same quality as native, which is unlikely. Intel stated, quote, "The frame is as good as the prior picture, the native frame, but it's actually being run quicker," end quote. We doubt this will be broadly true, and we'll evaluate it later on DGPUs. It was bullshit when NVIDIA claimed it too. The quality can be good, but it is rarely, quote, as good. Intel also had some other side-by-sides that we take issue with, and that, in combination with the fact that they still have watermarks on the press videos, means we'll just skip them instead and test it ourselves later. Intel referred to the FrameGen process as looking into the future. NVIDIA CEO Jensen Huang had similar delusions about NVIDIA's frame generation. Both of them are wrong, because all current methods of frame generation rely entirely on finished frames and engine data. These frames already existed and could have been displayed instead of holding them to run the frame generation in between. That isn't looking into the future. That's interpolating between 2 sequential snapshots of the present or near present. Until a predictive method of frame generation comes out, none of these technologies look into or generate the future. They, at best, interpolate the past. And that's fine, but we'd really like it if these companies could get their shit together and stop saying that they generate the future. MFG, represented on benchmark charts, has been a major and ongoing controversy, and it's been a misrepresentation of performance on NVIDIA's side of things. Intel, therefore, has a landmine in front of it. It's just up to them whether they step on it. Intel says that it commits to relying on base raster performance for claims without frame generation when it makes performance claims, and it says when it publishes numbers including upscaling or frame gen, those will be provided as supplemental to the base metric. We think this is a much better balance of promoting a capability without totally misrepresenting reality. It's up to Intel to maintain this, but this we think is a good start, at least based on how they described it. Intel also talked about a new version of PresentMon that includes a few changes, partly accounting for frame generation technology. We have a really in-depth breakdown of that coming up in our next video. All right, so that's it for this one. That's some of the Intel news. I had more, like I said, but that's stuff we want to kind of go over for now. And I think we're only going to test this stuff probably in handheld. So as handheld devices iterate with Panther Lake and with Xe3, we're definitely going to try and get some of those in benchmark. We actually have a handheld benchmark suite coming up. We're going to be looking at the new Lenovo devices and things like that, hopefully, as they come in. And so we'll be refreshing those numbers. And then whenever this actually launches, right now it's kind of just an architectural disclosure, but whenever this stuff launches in a handheld gaming device, likely the MSI Claw or something, we'll try to get that in as well. But otherwise, as usual, you're not going to really see much laptop coverage from us unless it's super interesting or out of the norm somehow. This is just setting the stage for future Celestial discussion, I think. And the animation error stuff that we've got back there, check back for that. It's going to be, again, pretty important stuff for some of our future benchmarks to try and understand it. And we'll talk more about that in the next video. But thank you for watching. To subscribe for more, go to store.gamersnexus.net to support this type of direct reporting. And you can go to patreon.com/gamersnexus for if you want to throw a few bucks our way and help us out. And thanks for watching. See you all next time.